Here's our third short answer paragraph from Unit 3. Car on a road with a circular hill. So you can look at the picture. You're assigned to do some calculations for a movie stunt that involves a car on a straight road. The road has a hill that rises 8 meters above the flat region. The top of the hill is a circular arc of radius 20 meters. You need to determine whether a car traveling under certain conditions will lose contact with the road at the top of the hill. There's a stop sign 50 meters from the beginning of the hill, and you're to assume that a car of mass 1,600 kilograms accelerates uniformly from rest at the stop sign. Has a speed of, when it hits the beginning of the hill, has a speed when it reaches the beginning of the hill, then coasts with the engine off. Assume energy losses due to friction and air resistance are negligible. So that was worded kind of weirdly, but I didn't have any trouble solving this, so let's move on. Find the magnitude of acceleration of the car during the first 50 meters. This is just a straight kinematics question out of Unit 1. So the delta x is 50 meters. The final velocity is 17 meters per second. Oh, that's what I'm not seeing in this problem. The velocity is 15 meters per second. I'm going to go check your copy. Okay, I just saw it on the diagram. That's the speed of the car when it hits the hill, 17 meters per second. So I'm looking for the acceleration. So I used VF squared equals VI squared plus 2A delta X. Okay, you notice that the other ones, both this one and the other one, both need time, so we can't do that. So using this formula, we get acceleration of 2.9 meters per second squared. So 1 point for the correct equation and 1 point for the correct answer. And this just reminds you, even though they do tell you a lot of things in the problem, looking at the picture also helped as well. Part B says, how long does it take to reach the beginning of the hill? So for that one, I just used the same one that I just crossed out. V final equals V initial plus AT, plugging in 17 here, 0 here, and the acceleration that I just figured out gives me a time of 5.88 seconds. That is 1 point for the correct equation and 1 point for the correct answer. Part C asks us to find the net force required to accelerate the car. So we know that the net force is equal to MA. The mass was given as 1,600 kilograms. We just calculated acceleration a couple of lines ago. So we get 4640 newtons. And again, 1 point for using F equals MA, 1 point for a correct substitution of mass of 1,600 kilograms. Part D says to draw and label the forces that act on the car at the top of the hill if it travels over the hill without losing contact. So we've got the weight of the car acting down and the normal force acting up. Again, if it doesn't lose contact, then there is a normal force, so we are all good. We get a point for labeling the normal force, a point for labeling the weight, gravity, and 1 point for no extra forces. So part E says calculate the minimum speed the car must have at the top of the hill to momentarily lose contact with the road. If you need to draw anything other than what you've drawn in part D to assist in your solution, use the space below. Don't add anything to the figure. That's more important if you're taking it in person there. So the minimum speed needed to lose contact, well, when that happens, the normal force is equal to 0. So then the net force, it seems weird to say this, but the net force is the object's weight. The car is actually in free fall at that point. So that's equal to the net force, which is equal to then mv squared over r, because at the top of the hill, we are working in a circle. So we have mg equal to mv squared over r. A little bit of algebra there gives us a velocity of 14 meters per second. That's the minimum speed that it can have to lose contact with the road. So 1 point for realizing that the net force is a centripetal force, 1 point for realizing that the normal force is equal to 0, and then 1 point for the correct answer with units. 3 points for part E. Then finally, part F says, what speed do we need at the bottom of the hill in order to have that speed at the top of the hill? So we're going to have bottom of the hill equals top of the hill. We're going to use conservation of energy. Okay, so going back to look at the picture, if we use the level or the lowest level achieved as h equals 0, we have at the bottom of the hill, we have 1/2 mv squared. We have no gravitational, so maybe I should write k plus ug equals k plus u. Whoops, u, it doesn't like when I write up there, ug. Okay, so that's the initial speed that we want there. The speed at the top of the hill is 1/2 mv squared plus mgh. Now over here, vi is what we're looking for. Over here, v is 14 meters per second. Again, even if you got it wrong in part E, if you substitute that answer here, you can have full credit. Over here, h is equal to 8 meters. So some more algebra gives you an initial velocity of 18.8 meters per second. The rubric says 3 points for this problem, 1 point for indicating conservation of energy, 1 point for correct expressions for conservation of energy, and 1 point for the correct substitution for part C. Again, even if your answer is wrong, that's okay. So 3 points for part F, and that's it for this problem.